Hi folks, and welcome to Open Analysis Live. Today we're going to be taking a deep dive look at this new ransomware called ESXiArgs, which is attacking a vulnerability in VMware's ESXi hypervisor, and it's worming its way across the internet, ransoming all kinds of different hypervisors. I can't remember what the count is now, but it's a massive number of servers that have been impacted by this. And to help us figure this out, we have a special guest. Fabian is joining us today. For those of you who don't know Fabian, he is probably one of the #1 ransomware crackers in the industry. I think he's responsible for breaking more ransomware than anyone I know of, at least. So we have him on, and he's going to walk us through step by step through how this ransomware operates. Just a heads up front, I don't want to have any false promises here. It turns out that there are no crypto flaws in it, so it can't be broken. However, there is a way that you might be able to recover your data if you're watching this video. I will put a link down below. Sometimes when this ransomware is deployed, there's a bug with how it's deployed, and it may not encrypt all of the files, so they might be recoverable. So I'm going to link that below if that's why you're watching this video. Otherwise, stick around and we'll be talking to Fabian about how all this works. Also, obviously, it wouldn't be an OALabs video if I didn't shill for our Patreon. We have a video up there where Fabian takes us through a real-world example of ransomware which is vulnerable, and he shows us how you can attack the cryptography and break it so you don't have to actually pay the ransom. If you're interested in that kind of stuff, go check out our Patreon. If you want to see more about ESXi, stick around and let's get into it.
Okay, so let's take a look at ESXi args real quick.
Sweet.
So ESXi args, it contains of like two parts, at least two parts that I know of so far. It's a shell script and it's a binary. So I suggest we would start just with the shell script first, I would say. And
Nice ransomware,
yeah.
bro.
Oh yeah, those are their commons. Yes, this is like a file exactly as it was deployed by the ransomware threat actor. My guess, I mean, right now it seems to be there are like more than 2,000 servers affected by this. This is clearly like an automated attack, right? There's someone set up like a script who just does it automatically, deploys the ransomware payload, like deploys these scripts, and then just goes off and let it run. Scan the whole internet and pop a couple of thousand exposed ESXi servers. Yeah. Okay, so let's see what we got here. So they're defining like a just a variable temp as like a, honestly, for like 95 to 99% of all cases when you deal with an encrypted ESXi server, the ransomware payload is to be found somewhere in temp. Just from experience, people just, or threat actors, they just upload it there and then run it. And that's it. They seem to be increasing like the certain limits a little bit. Yeah, makes sense. So they don't run into issues where they can't open new files because they had like the file handle limit, for example. So next they are running ESXCLI. ESXCLI is like a command line tool on ESX that you use to interact with the VMs, and it's essentially like a proprietary tool. And it does appear like they run ESXi CLI VM process list. I would assume that gives you a list of all the VMs that are running, and then they are grabbing for like config files. So without an actual ESXi system to run this, but I would assume that this will give you like a list of all the VM configuration files on the system, like all the VMX files of VMs that are running on that particular ESX server.
So they're trying to get the path to the
path to where the virtual machines are stored, essentially, like where these configurations are being stored. Okay, then they stop the, oh sorry, voice crack. Then they stop the VMX files. Then they are stopping the running virtual machines. It's kind of interesting that they're using like kill, because I'm pretty sure there's like an ESXL CLI command to shut down the VM gracefully.
Kill
instead of
-9.
just killing
No
the
more-
process.
No more CPU time.
I've got your fucking PID, and the bottom line is that you best not front, or it's kill-9. Kill-9, no more CPU time, cause it's kill-9 and your process is mine. Kill-9, it's my time to shine. Don't step out of line or else it's kill-9.
That is true, yes. Then they are making another file executable that is like this encrypt file that we have here as well. They then seem to enumerate all the different storages that are being configured. ESXi has this concept of data stores and data storages. So yeah, those are essentially the locations that will actually host the virtual disks and the configurations and stuff for you. As you may be aware, when it comes to virtualization, like the time where each server had its own local storage are long gone. Usually you have like some sort of network attached storage that's like super fast and that is being used by like multiple servers at the same time, stuff like that. And then appears to be grabbing everything that's like mounted in the volumes folder. This is, by the way, the default folder where all the data stores are being mounted in ESXi by default. And it seems to be essentially like iterating over all these different volumes, right? So each volume has a name. So this is to essentially get the volume name, and then it uses find to enumerate through all the files in each data store. And it's looking for anything that's of type F, which means files, and it needs to have like one of these file extensions. So essentially, they aren't going to do the enumeration within their ransomware themselves. They are embracing the Unix principle of everything should only do one job, and then you just string like dozens of tools together in order to create your makeshift shitty ransomware, right? I'm surprised they aren't using like the OpenSSL command line tool to do the actual encryption. Yeah. So yeah, but we can clearly see here that it's like getting all the files that are ending or that contain the following extensions. So this check over here just makes sure that the file actually exists. I don't know why they are doing this, but who knows? They seem to be getting the file size, offset file, in kilobytes, it seems. With like the -k, I think, gives you the file size in kilobytes. They then appear to check whether or not the size in kilobytes divided by 1024 is greater than 128. So this is essentially, so what this check pretty much does is, hey, is this file bigger than 128 megabytes? Because, yeah, 1024 kilobytes are like 1 megabyte, and then greater than 128, yeah. So they are, for files greater than 128 megabytes, they seem to be setting this particular size step variable. Otherwise, it's being initialized with just 0. And usually in ransomware, when you see something like this, oftentimes ransomware has like certain thresholds that after a file reaches this particular threshold, they are not going to encrypt the whole file to save time. They may only encrypt like certain parts of it, or they may encrypt a part, then jump a little bit further, and then encrypt another part. So this is what I would assume is going on here. But we will see later what exactly is going on. And then it prints out like a little bit of... and size step is the size in megabytes, 100 megabytes minus 1. So, okay. So, 100, yeah. It's the size. So, it seems to be, the size steps seems to be like in steps of like 100 megabytes of some sort, and this seems to be like some sort of maximum. So if a file is like 900 megabytes, for example, then this value would be 8. Because 900 megabytes, then, yeah, 109, yeah. Okay, so I would expect, so this is like 8 in that particular case. It's just like some sort of arithmetic. And honestly, like figuring out these custom chunking algorithms when they are being used is often what takes the most time when it comes to breaking ransomware, because some ransomware authors get like very creative when it comes to these specific algorithms. It's not always, oh, we are just going to jump by a fixed amount and then we will just encrypt another fixed amount and then jump by another fixed amount. Sometimes it's like the result of like rather complex equations. Sometimes they also make errors and mistakes in these equations. It's a horrible mess sometimes. Yeah. And last but not least, they seem to be running this encrypt file, passing in a public.pem. So this is like an RSA public key. PEM is like a popular format for that particular case. The file name, then whatever they have calculated as this step size, 1, and the file size essentially, because size in KB times 1024 is like the size in bytes, right? Okay, so let's check out the actual encrypt binary. I'm not sure yet whether or not there's going to be a private key reveal party, but we will see. Now, the great thing about ESXi and Linux ransomware in general is that ransomware threat actors haven't caught on to the fact yet that release builds of Linux and ESXi binaries still contain symbols. So I wouldn't be surprised if yes. So this contains like full symbols. And we have two choices now, chat. Do we want to use those symbols and potentially see whether or not the threat actors made embarrassing typos when naming their functions? Or do we want to have at least a little bit of challenge and not use symbols at all? Okay. Okay. So,
back to source.
So, okay. We are using symbols. It's honestly, sometimes they have like really weird typos in their code, and it's nice. So, okay, one person is asking for hardcore mode. What shall we do?
You can do hardcore mode on your own time.
Yeah, I will do hardcore mode on my own time. Okay. So, yeah, and we can see like, let's check out like the function names first to see if there are like any weird function names in there. Print error x, get file cur size, get pk data, create RSA object. Man, those guys are really lame when it comes to names. Oh, we have French people represent your French stream, or like, yeah, your French stream cipher is being used by them. There's only one other ransomware family that is using that particular stream cipher, and that's Barbuk. So I wonder if this is like somehow based on the Barbuk code, because there's like no real reason to use like French engineered encryption and algorithms.
Did Barbuk have a Linux version?
Yes, they do, and the Barbuk source code was leaked. So you can see them. Yeah, I agree with Rothry. If they wanted us not to use symbols, they would have stripped the binary.
Well,
and yes, Noxic, that is usually what happens quite a bit, that they forgot to strip the binaries, because release builds by default still contain symbols on most Linux-based toolchains.
I've noticed, I don't know, I mean, you looked at a lot more of the stuff than I have, Fabian, but like I noticed there's a skill difference between people who are writing Windows ransomware and Linux ransomware. Like, I think the first
yes, certainly is, yes.
Yeah, like the first Linux ransomware I looked at, it looked like they could barely get it to work. Like, I didn't think, it seemed like they weren't familiar with how to write software for Linux.
ESXi, to be honest, is a special beast in particular. So early versions of ESXi, I think versions prior to version 5, it was still called ESX back then. They were actually they were using a Linux kernel. So they used a Linux kernel to boot up, and then they replaced the Linux kernel using their hypervisor. Now, ESXi, starting with version 5, I think, or maybe even earlier than that, but when they changed the name from ESX to ESXi, they also changed the kernel they are using. So they are no longer using a Linux kernel. They use their own kernel called VM kernel. And VM kernel is like a very kind of bizarre thing. Technically, it implements the syscall ABI of an old Linux kernel. So there's like a certain degree of compatibility.
Yeah.
But it's not 100% compatible. And even the Linux ABI or like the syscall interface that they implement is like based on I think 2.6 something. So it's like ancient. We are talking like over a decade old. So that poses a whole lot of challenges when you want to compile any binary for ESXi, because there's essentially no documentation. It's not something that VMware wants you to do. They don't want you to do this. And in order to get this to run, is a challenge in and of itself, because it's not as easy as just, oh yeah, I'm just going to statically link glibc into my ransomware, and then it's going to run. It's not that simple. There are a lot of very subtle issues with that, and a lot of cryptography code just breaks. And as a result, oftentimes ESXi and Linux payloads, as a consequence, are often vulnerable to certain flaws or like to certain attacks that their Windows counterparts are not vulnerable to, even though both of them are compiled from the same code base. So it's quite interesting what is going on over there. So Peter was asking whether or not they have to statically link everything that they want to bring along then. Yes, a lot of ransomware actually does that. So they do link everything statically. The problem is, and that is something that a lot of people are oftentimes not aware, glibc is not designed to be linked statically. glibc will break horribly if you start mixing numbers, or if you do anything that causes the real glibc from the system to be loaded inside your statically linked process otherwise. And the problem is that there are a lot of APIs that will load glibc that is on the system without you noticing it. For example, when you do DNS lookups, it just loads glibc, even if it's linked statically, it doesn't matter. So it's not as easy as just like linking glibc statically. What you would want, well, I don't want to give them tips how you do it properly, but yeah, there are a lot of subtle bugs, and it's not as easy as just, oh, let's just link stuff statically and things will work out. It's unfortunately not that easy. So
all the chain fun, and they still forgot to strip the symbols.
Yeah. Yeah, Cerberus, rename your main user to Windows. I mean, that reminds me of like this incredibly dumb recommendation to, just install like the Russian keyboard layout and then ransomware so it does not affect the system. Which honestly was being promoted as like a real like workaround a while ago, and it's just the most stupidest thing ever, because usually ransomware doesn't check what like an install keyboard layout is. They check what the default keyboard layout is. So unless you also want to roll out Cyrillic keyboards in your company, this is not going to work. I'm sorry, it's just not. And even if it was, like, the thing is, ransomware nowadays, at the time the ransomware is deployed, the attacker knows pretty much everything about your company. They know whether or not you're a real Russian company or not. It's
They
it's
knew
not
that
going
like
to
a month
happen.
ago when they first got in.
Yeah, when they first got in, and they probably know your network better than you do. That's just the reality. Oftentimes, ransomware threat actors spend like a week, sometimes even multiple weeks inside your network, mapping out your entire network, figuring out what are like the high-value targets within your network. They want to exfiltrate data first before they encrypt stuff. And most ransomware families, yes, while they do have like a check for the keyboard layout, for example, that check can often be disabled using just a config flag, right?
Yeah.
So it's a completely nonsensical sort of fix, and that people are promoting.
I have a fully anonymized, for everyone watching, story about something very similar where um, you could watch the operators, so the people who are actually deploying the ransomware, testing the AV at the victim to see what it would stop, and then modifying their payload so it would work live within the network. So this was a long time ago. I think things have changed a little bit and how this works. I think deployment time now seems a lot faster. I haven't been looking at intrusions for a while, so I don't really know what the state of the art is now. But 4 years ago or so, 3 years ago, yeah, it was pretty much they would just test it and see it doesn't work. this this security solution is blocking it. Well, let me try something new. So it was always kind of weird when people would say, like on the security teams, they'd say, "Oh, well, we're going to deploy this protection against ransomware and this protection against ransomware," when really you want to deploy a protection against somebody sitting in your fucking network. Like that's really what you got to focus on here, not the ransomware payload. That's by the time that comes, it's all bets are off.
Yeah. I mean, from personal experience, they still spend. It has gotten a lot shorter, but most families will still. They're almost always signs like 3 to 4 days ahead still.
Okay.
So you still have like a 3 to 4 day head start to stop the attack before the ransomware is actually deployed.
Okay. All right.
But as you said, it kind of depends. There's still a lot of threat actors and groups out there who will take quite a long time before deployment. Others, they oftentimes automated the entire process to a point, including the exfiltration.
Yeah.
Where you have like specialized exfiltration tools. They optimized it and automated it to a point where the ransomware deployment happens within 24 hours of the initial access, right?
Yeah. I saw some public reporting on some of that stuff, which is what made me think, oh, maybe they've sped up the deployment time. But yeah, I guess they're still doing some people are still doing the long dwell time.
Yeah. It also always sort of depends whether or not the initial access was whether or not there's like an initial access broker involved who sold the access to the network, because that takes time usually.
Right.
Or if the group who is deploying the ransomware is also the group who is getting or arranging the initial access, right?
Yeah, whether it's affiliates or not, and yeah.
I fully agree. Okay, let's go back to this amazing ransomware though. Right? So yeah, it's so this is like what command line parsing looks like when you're a shitty programmer and you're restricted to C only. So it seems to be initializing like the local installed libssl. So yeah, they are using the available OpenSSL library. So what are they importing? So for those who've never looked at like a Linux binary or something, dlopen is like the Linux equivalent to load library to translate it to Windows terms, and like dlsym essentially looks up a function by name. So it's kind of similar to getproc address in Windows. Yeah. So it's looking up your memory buffer, so memory stuff, memory allocation stuff. Oh, so we are dealing with RSA here. They're also using the OpenSSL random number generator, rand pseudobytes. They're using RSA public encrypts, and there's also RSA private decrypts that are being imported in also RSA size. So we are dealing with RSA here, most likely. And we also saw earlier that they are using like Sosemanuk or Sosmanuk or however it's going to be pronounced. Which, as I mentioned before, is like a stream cipher. So my guess is they will probably use Sosmanuk to encrypt the actual file data, and will use RSA to then encrypt the file keys that they probably generate using run pseudobytes, and then attach it to the encrypted data, to the encrypted files. But we'll see. So first of all, they get all their function pointers in order, so everything's fine. If that fails, then they will just return an error, which is to be expected. Then they appear to be opening, so the first parameter, they appear to be calling like the get pk data. When we look in our script again, the first parameter was our PEM file, which is essentially most likely containing our private key. I unfortunately don't have the private key, the public key. I unfortunately don't have. If I had the private key, that would be great because we can decrypt all the data, right? No, I unfortunately don't have the public key file, so I don't know what key size exactly we are dealing with. So we'll see. Anyway, let's go back. So yeah, this opens. So this is like our key file. So it opens our key file. We get a file descriptor back. It checks for errors. Then it seeks to the. See, what is seek end? So it seeks to the end of the file. So lseek gives back the offset that you end up at after the seek operation. So this is essentially a way to get the file size, right? You seek to like the 0th offset relative to the end of the file. So this is like our file size. Then it checks if our file size, so this is like classical error checking again. If we got back a valid file size, then it's going to allocate a file size plus 1 memory, bytes of memory. Then this is seek set. So this seeks to like an absolute offset inside the file 0. So this seeks back to the beginning of the file. And I would assume, yeah, so they are going to read the file data. And that's it. So that file pretty much does exactly what the file symbol told us. It essentially just reads out. So that's like the
symbols are amazing.
Yeah. Although sometimes, like, I don't know, because of incompetence, but sometimes the functions do something completely different than the name would suggest, right?
Yeah, that's true. But somebody mentioned in the chat too the helpful error messages that they print, so they have logging.
Yeah. Error messages are thumbs up right there. So that's like the key data. So I would assume that then is the RSA object, because they are passing in the key data that is still PEM encoded, which is like base 64 and stuff. And they are creating like an RSA object, and that's just a guess right now, but let's see. So they are allocating some memory. Yeah, and then they just call read. Yeah, so that is exactly. So this essentially just decodes the PEM encoded RSA key and returns you like the key object that is then being passed in. So name checks out, everything's fine so far, and then they just call encrypt file. Oh, and oh wow, they have a help screen. Wow. So, okay, the first is the public key, then the file name, then the encryption step. Number of MB to skip while encryption. Number of MB in encryption block. And then we have the file size in bytes. Okay.
So they're encrypting in 1 megabyte
Amazing.
blocks? Is that what we saw?
Yes. So this is how much they skip,
Yeah.
right? So
That's why it's a -1 then. That makes sense. And then they're
Yeah.
encrypting one megabit.
And then they encrypt 1 byte, and this is like how large the file is ultimately.
Yeah. So they only encrypt
So
1
for
megabit.
a 900, for like a 900 megabyte file, they would encrypt 1 megabyte, then jump 8 megabytes, then encrypt 1 megabyte, jump 8 megabytes,
Yeah.
because they like the size step is like yeah, the size in KB divided by 1024, so you end up with megabytes, and then divided by 100, and then
No,
so
it's definitely
yeah.
not restorable. You can't encrypt
No.
1 megabyte blocks every 100 megabytes. And
if you lose, like it's not restorable.
Yeah.
That being said, in a lot of cases where this was deployed, something like the script broke or the binary broke, so the actual only the VMDK files but not the VMDK flat files got encrypted.
Oh.
So these VMDK files, they only contain some information like, oh yeah, the data is stored in these VMDK flat files.
Yeah.
And like a GUID and some other metadata essentially. So the data is still there and it's not encrypted, but like the definition files that define the storage, they are gone, but they can be recovered in many cases.
Yeah.
So that is, if you are affected by this, then there is hope. For a lot of people, only the metadata got encrypted, not the actual data on the virtual disks, and there are instructions floating out there on how you can recover those. If you're affected, I would suggest going over to Bleeping Computer, really. Bleeping Computer is like shout out to Lawrence, definitely. Bleeping Computer is like the place to go to if you're affected by ransomware, if you need help dealing with it. And it has been for over a decade at this point, right?
Yeah.
And it's totally free. Like you don't need to pay anything, right, to register an account over there and ask for help. We can actually check out the. I think they have coverage. Oh yeah, here. Yeah, there you go. And he outlines the exact the steps that you can take in order to recover the metadata. And restore your VMs if you're affected by this. And I would suggest be careful, make backups of your encrypted data, right? That's always important. Like an encrypted backup is better than no backup at all. And there have been many, many cases where decryption tools actually, both threat actor encryption tools as well as encryption tools provided by like other parties, damage data during the actual encryption process. So there we go. Let's go back in here. So yeah, the encryption step. This is how many is being skipped. Also, why it's like 0, right? For smaller files where it's always 0, it will just encrypt the whole thing. Yeah. Less than 128 megabytes. So yeah, let's see. So we know. So this is like our encrypted size. Do we have anything else? So the third parameter, that's like our encryption step. That's the encryption chunk size. And that one was the file size. There we go. Oh, one thing. Why are they passing in the file size as like a command line parameter? Does anyone here have an idea why they might do this? Any guesses from the chat?
Chat's delayed by like a couple seconds.
Yeah, I know. Yeah. Don't worry. I have been in your top 2% of chatters.
Of chatters, yeah.
Yes. I was so proud. Any guesses why they may pass in the file size from the outside?
I have a guess.
I mean, yeah, you don't want to hard-code a file size, but you could totally like just get the file size like they do getting the file size for the RSA key. Seek to the end, know where you seek to because it's being returned by the seek API, and then go back to the beginning. I mean, yeah, Peter, that could be right, but then again, they know how much they append to the thing, so they could just calculate it. Okay. Any other guesses? You have 30 more seconds. Usually, you don't run antivirus software on ESXi.
No, that's a bad idea.
And a default size. Yeah. So the reason is that ESXi allows for something called thin provisioning.
Yeah.
So those VMDK data files on disk might be a lot smaller than the disk they actually represent, because the VMFS file system only stores the areas that have been changed.
That they need, yeah. Or sorry, that have been changed. Yeah.
Yeah. So that is why they use like this ESXCLI tool in order to sort of figure out how big this stuff is, because it's yeah, it's like not exposed through a normal API. It's something that's specific to ESXi and VMFS in particular. Yes, exactly. They are passing in the maximum file size that this file could be instead of what it actually takes up on the disk.
For all you EDR developers, definitely take a look at ballooning file sizes, ballooning disk usage on your ESXi drives. That might be a good tell.
100%, yes. Okay, so we let's fix up the names here. So the first one is like our file name, although God knows if it's actually going to take.
If it's gonna work or not.
Ida, why are you? Sometimes Ida is just stupid. Let's be honest. I mean, for software that is like so. I mean, I know you have the same opinion than I do
when it comes to Ida. Relationship.
It's for something that's like so expensive, you would expect something like renaming the variable names to work. Yay! It took.
It did work.
Amazing, amazing. So let's see, what is it doing? So it opens the file for read write, which is something you would expect, right? So we are getting our neat little file descriptor here. And that generates a key stream. Or, oh no, a stream key, not a key stream. And this is like this, it's like a stack variable, 40 bytes in size. It's generating like 32. So let's see how it's being generated. And yeah, does use like rand pseudobytes, which is an OpenSSL. I think it's actually like a deprecated OpenSSL function. And I think they are actually using it incorrectly here. Let me look up the OpenSSL configuration. Yeah, we know that it was deprecated. We still need the man page though. That's like the sort of issue that you will get into when you deal with ESXi, since their stuff is like so outdated. Oh yeah, so pseudorandom bytes to the buffer, pseudorandom byte sequences generated by pseudorandom bytes will be unique if they are of sufficient length but are not necessarily unpredictable. That is not something you want to hear when it comes to your key generation function.
Not
they can be used for non-cryptographic purposes and for certain purposes in cryptographic protocols, but usually not for key generation. Okay. So random pseudobytes returns 1 if the bytes generated are cryptographically strong, 0 otherwise. Both functions return -1 if they are not supported by the current rand method. So.
Right.
This checks if the value is 0 or non-zero. So if so this is true both if the random number generation failed entirely, or if the returned random numbers are cryptographically secure. It will only fail in the case where the cryptographic key material it shouldn't be used for cryptographic operations. So
if it fails completely, they'll just go on ahead.
Yes, it will just go on ahead and move on with whatever was in that memory in the first place.
Null bytes.
So, thumbs up, thumbs up. Oh, by the way, in case you're curious, why would this fail? Why would like any random number generation function fail, right? There are different types of like random number generators. There are true random number generators who are usually based upon some sort of physical phenomena, atom decay, for example. There's something called LavaRand at Cloudflare, where they have like this huge installment in their US office of like hundreds, if not thousands of like lava lamps. And then they like record the movement of the lava lamps in order to get like true random data and true random information.
Amazing.
But the amount of entropy, like the amount of information, like truly random information that you can generate is pretty much limited. So you can only get like, what are you doing, kitties? Wow. I'm sorry if you can hear the cats in the background. They're like chasing each other all through the apartment right now. So the amount of like true randomness that you can collect at any given time is gated. So usually what you do is you use these true random number generators to generate seeds for you. And these seeds are then used in order to seed a different type of random number generator that is called a pseudo random number generator for you. Yeah. Blue or Black is posted like a picture of the lava lamp. So this is actually being used by Cloudflare to generate the key material for SSL handshakes. It's quite cool. There are a couple of YouTube videos out there that you can check out if you're interested in how exactly this works. But the idea is that the physical phenomena that is responsible for the pattern within the lava lamp, they are assumed to be very random and unpredictable. So essentially they are recording this huge wall and use the image data in order to turn that into encryption keys. It's pretty cool.
Yeah.
Okay, back to this. So there are two different types of like pseudo random number generators. They are cryptographically secure random number generators. They are called CSPRNGs. And they are insecure pseudo random number generators, like the rand function in the C programming language, for example. Now, the problem with these pseudo random number generators, or in particular with the cryptographically secure pseudo random number generators, is that if you don't seed them correctly, the random data they are generating, the keys they are generating, they will still end up being insecure. A couple of years ago, there has been like a huge fuck up in OpenSSL, specifically in the OpenSSL package used by Debian, where they managed to fuck up the initialization of the OpenSSL CSPRNG so bad that there were only, I think, about like 32,000 possible RSA private keys that can be generated for any given key size. And yeah, I mean, the whole reason was that someone was running Valgrind on like the OpenSSL package and saw, oh, this is like accessing uninitialized memory. Let's initialize with like something proper. But that uninitialized memory was like one of their entropy sources that they used to essentially seed their random number generator with, right? And the result was, yeah, all the keys generated by that particular version of OpenSSL were completely broken, and you can no longer use it. So even if you use a secure random number generator that is designed for cryptographic purposes, you still need to make sure it is being seeded properly.
Yeah.
And this is essentially, and my guess is random pseudo bytes may have like a fallback if there isn't enough true randomness available to seed their CSP, their cryptographically secure random number generator. They will probably return random bytes with, oh yeah, those are random bytes, but please don't use them for cryptographic purposes.
Yeah, which is kind of a dangerous architecture.
It is. Yes.
Yeah.
And I think that is probably also why they deprecated this particular function and moved to rand bytes. Because rand bytes, either it gives you cryptographically secure bytes, or it doesn't give you anything.
Or nothing. Yeah.
So, which is the way better design. Like, don't use this, but they probably had to use it because there's like an ancient OpenSSL version available on ESXi only. Okay, so this gives us like our random key. So that's like our key buffer. And then it's next it seems to encrypt our RSA, our key buffer using RSA. Classic, really. RSA public encrypt totally makes sense. It's like the it's using like the public key to encrypt the data. The key buffer, that's the size. So let's see. It's like a public key object. The second one is our buffer that we want to encrypt. The next one is like our buffer size. And then those other two, I would guess like this probably is like our encrypted buffer. And this one is like the our encrypted buffer size. Yeah, I don't know yet for sure, but those are like educated guesses. We can look up the documentation in a bit. So that is like all being passed in, essentially what we would expect. Let's see, our encrypted buffer. Yeah, it's like allocating some sort of memory. This RSA size probably gives you back what is like the maximum size of data that this RSA key can encrypt. So an RSA 1024 key, for example, can at maximum encrypt 1024 bits, or in that particular case, 128 bytes, right? So there's like a size limit for RSA, how much data you can encrypt in one go without having to chunk the data or do something else, like split it up into different smaller parts. And for RSA, that's determined based on the RSA key size. So let's see. I would expect this to return the. Let's see. Can we do it here? No, it's not found. So
Google.
and also, it's once again, it's like a deprecated API. So thumbs up for that. Yeah. So it returns the modular size in bytes. It can be used to determine how much memory must be allocated for an RSA encrypted value. And the other one is RSA public encrypt. Can we just plop it in there? Yeah, we can. So it's like the length, the from length, then where it's being encrypted to, the RSA object, and the padding. Let's see, is that essentially? Yeah, the length, the buffer that we want to encrypt, where it's being decrypted to, our public key object, and this is like the padding, I think. Was it the padding? Yeah, the padding. And padding of 1 is probably PKCS 1 padding. Don't use PKCS1 padding in general. I mean, they also say it here. It's most widely used mode. However, it's like highly recommended because there are like certain attacks that you can do, like padding oracles. If you want to go down that route, you may want to look up the Bleichenbacher attack. There are like certain padding oracles, and in the past, like PKCS1 has been the downfall for many times when it comes to SSL in particular.
I think if we get into padding oracle attacks, our viewership will drop to like 1.
Even further.
Rattle. Just one guy.
Yeah, it's Rattle. Rattle, finally they're doing the stuff I'm interested in, right? So yeah, this is like very much encrypting the key buffer using RSA. And then it calls this neat little function, encrypt simple, and it gets back. Yeah, there we go. So it gets the file descriptor, the file buffer, file size. So let's see. Yeah, and here you can see it's like initializing the Sosemanuk key schedule essentially. Probably passes in. Let's see. Let's rename those real quick. File descriptor, the encryption step, the chunk size, the key buffer, the key size, and the file size. So let's go in here. Yeah. So this v14 seems to be like local array of like 400 bytes. This is probably like the context, kind of like a structure that contains like all the information to like where's the key stream at the moment, stuff like that. Then we have like this init thing. Let me see. I wonder if we can actually find the
docs for it. I'm not familiar with this cipher at all. Never seen it before.
Yeah, as I said, like the only ransomware family that I am aware of that uses. Oh, so that's suddenly gone.
Wayback Machine that.
I was just going to say.
Hey.
Yeah, I have a feeling they took exactly this code.
I wonder why it disappeared.
You heard it here first. Like this is like
that's the developer.
No. I'm not saying that. I'm not saying. I was just joking. Oh, so it okay. So this is just a copy taken from someplace else,
Something
like from
else.
the eCrypt. Yeah. So there. I don't know if it's still ongoing or if it was in the past. So the EU is currently trying to standardize stream ciphers and also post-quantum cryptography. And eCrypt is, yeah, it's like this.
Oh,
so this is probably the Sosemanuk code that was submitted to the eStream competition in order to be selected as a potential new official stream cipher for the EU. So that's probably where they took that code from. Okay, yeah, that makes sense. Also, Barbuk is using the eStream code, like the eCrypt code. So yeah, it's probably that. So yeah, it checks the file size. If the file size, oh, so they still get like the current file size. That's interesting.
Weird.
And they check if the file size is smaller than the current file size, and if it is, it's being adjusted. They then allocate buffer. I think that should be, yeah, that's 1 megabyte. So that's probably the file buffer that they are operating. Yeah, the encryption buffer. We can. Kind of weird because they are also, see, they are like also passing it in. So, oh, so they are doing it. Okay, so this is actually just like a file buffer that is being reused, and they are also using like the chunk size in order to like do multiple reads and writes using the same buffer if the encryption chunk size is like more than 1 megabyte, it seems. So yeah, once again, they are like reading the data into up to like 1 megabyte into the file buffer. And they are going to encrypt it. And then like with the Windows ransomware, so this is like our secure, they correct the file pointer, like rewind it to the original position from where they read the data. And then they are going to write it
sandwich.
out. The ransomware sandwich, as Sergey aptly named it, right? So like this sort of pattern you will see all the time when you deal with ransomware. Like it reads the data, it calls like some function on it, it rewinds the file pointer, then it writes it out again. That's just...
I haven't seen anything crazy here besides the funny not checking if the RNG failed. I haven't seen anything else here that's crazy though.
I mean, there's a chance like a lot can go wrong with generating RSA keys. There are a whole bunch of things that you can do wrong. However, given that this code is using OpenSSL, I would assume they also generate the RSA keys using OpenSSL. And OpenSSL generates proper RSA keys. Like, unless you use the Debian version from like 2008, right? Then it doesn't. But in all other cases, the generated RSA keys will be secure. So overall, also, it generates like a new key for every single file. So there's like no key reuse between files or within a file, for example. So yeah, this would be like a sample, unless we could find the private key somehow, or something went terribly wrong with the generation of the RSA key. This would be something that is secure, that we can't really do anything about.
Yeah.
So sorry, but luckily for all the ESXi ARGS victims out there, the ransomware kind of screwed up. Like the invocation sort of screwed up and it crashed all over the place. So there's a decent chance you can use this to recover your data. Do like data recovery the old way, or the hardware, the difficult way, the old school way. So yeah. Okay.
So I guess that's one good example of stuff you can't crack. So
yeah. Honestly, that is also like a pretty neat sample of like an ESXi ransomware.
Yeah.
If you want to get into analyzing this, because it's like very much straightforward, and you have the symbols.
Yeah.
You have the symbols, right? If you want to practice on your own, going through this, try to understand what is going on. It's absolutely an excellent sample.
All right, that was a long video, but I thought it was interesting. I don't know about you guys. I think this stuff is very fascinating. So hopefully you enjoyed it. And again, big thank you to Fabian. Go check him out if you are dealing with ransomware. He might be able to point you in the right direction. I put some links below, again, for resources that might be able to help you if your files have been encrypted. And lastly, of course, a shill for our Patreon. Go check it out. If you like this kind of stuff, we have a couple more hours with Fabian talking about breaking ransomware and tons more reverse engineering content there. All right, until next time, keep exposing the mechanics behind the malware. Stay curious.